Selfish routing can cause suboptimal outcome to many or even all the players in a routing game. We have seen this in Brace paradox, but in fact, it can happen in even smaller examples on just 2 nodes. Players want to go from A to B and have 2 different route choices. So in this example, there are 500 players as before, and 2 route choices, one which always takes 50 minutes, and the second one that takes x over 10 minutes, where x is the number of players. The unique Nash equilibrium in this game is for all the 500 players to use the congestible pass, taking 500 over 10 equals 50 minutes. And in fact, this is indeed a Nash because there's nothing they can do. The alternate pass also costs 50 minutes. But in some sense, this is not the optimal solution. We could split the traffic and send 250 people on each of the 2 different options. This would make the travel time for the 250 people who chose the 50-minute pass the same 50 minutes as before, but improve the travel time for the other 250 people to 250 over 10, which is 25 minutes, quite a bit of improvement. So what happened in this improved solution is that we made it better for some people without making it worse for anyone. And in particular, we decreased the average travel time from 50 to 50 plus 25 over 2, which is 37.5. In fact, this is the smallest average travel time possible in this particular network. It's nice, but it's not clear how we can convince users to choose a longer pass. That doesn't help them, it helps others. Unlike in the Bayes paradox, we can't just improve the situation by deleting edges. If we delete any one of the 2 edges, the remaining edge can carry the traffic, but it doesn't decrease the time. One way to help is to discourage people from using the congestible pass by putting in tolls or additional expenses, and maybe using these tolls to subsidize other people who have to use the longer pass. So tolls or even rewards like subsidies can be implemented via highway tolls. To think about what this does to people's interest or choices, we need to think of travel time expressed in money. So maybe the money that people are willing to pay for saving time in going on a faster route. So cost expressed in money, I use the same example again. There is a 50 fee for one pass and an x over 10 fee when x people use use that choice of a pass. And what we're going to do is add an additional cost to the congestible pass and a reward for people who are using the non-congestible pass. And the optimal reward and fee number here is 12.5. So let's assume we put in this additional cost or reward. So on the non-congestible edge, the cost used to be 50, and now we're giving a reward of 12.5, which makes the cost come at 37.5, and that's the cost of the lower edge. On the upper edge, you have a function that expresses cost in terms of the congestion, or the number of people who choose that pass, x over 10 plus 12.5. Where 12.5 doesn't depend on the congestion, it's just an additional reward everyone gets on that pass. So this changed the cost function, or the people's incentives, and now the unique Nash equilibrium is in fact to split the traffic 250 people going on each of the 2 passes. The travel cost on the lower edge is obviously 37.5. On the upper edge, it turns out to be also 37.5. There are 250 people, so x over 10 is 25, plus the 12.5 additional cost comes out to be 37.5, exactly the same, and indeed this is the Nash equilibrium. It's interesting to think about how much money this cost to institute this kind of solution. So on one edge, the congestible edge, we're collecting money. The tax collected is 250 people, each have to pay an additional $12.5 comes out to be some number. On the other hand, the non-congestible edge, we're offering a subsidy to people, and in the equilibrium, there are 250 people on that pass too, and the total subsidy is 250 people times the 12.5 subsidy we offer there. And you might notice that the tax collected equals the subsidy. So what happened here is that with taxes and subsidies, we could help improve the solution. We improved the unique Nash equilibrium, which used to cost 50 for everyone, to an equilibrium which is only costing 37.5 to everyone. And we did that without actually any cost. That is, the total cost of subsidies and taxes is actually came out to be 0. 250 people got a subsidy, a total of over $3,000. But the same amount over $3,000 is collected in tolls, so it comes out to equal 0.